of those.
How many people are unable to come to class?
Oh dear, it's quite a few. Is that because you didn't know that it was a 2-day affair, or you just, irrespective whether you knew, wouldn't have mattered? You can only afford 1 day.
I know.
I have one thing.
Yeah, okay. All right. So what I want to do is to demonstrate at least one app. We've got about 25. Lindsay will take you through an overview of our main site, GeoSci.xyz, as well as some of the things that are on, and also show you, a bit more about the apps and how to use them and how they're constructed. I just want to show at least one so that you get a flavor for what this is. And here's one it's DC resistivity, and actually can help. I don't know, it kinds of shows a typical scenario of what often happens. I've been approached by numerous people, and especially after doing DC resistivity, they'll say, "Well, okay, can I use DC resistivity to find a tunnel?" Right? So if somebody asks you that question, what's your response?
Yes.
Yes, maybe, and. So how do you tackle the problem of yes, no, maybe?
Run a forward mold.
Pardon me?
Run a forward mold.
Yeah. So you need to know some details about what they're looking for, right? So in this case, so let's suppose somebody asks you that question. I've got an app here that is 4 electrodes plus a target cylinder, and you can change the background resistivity of background, also change the resistivity of the target, and then the app allows you to work with all 4 electrodes. You can put the A and the B electrodes wherever you like. It's similar to the M and N. So that's these. And then if we're going to do some forward modeling, what are the things that we need to know? Okay, how about the background conductivity? So what would you like to specify for that? Anything typical here? Oh, somebody. A background conductivity.
500 today or 1,000.
Okay, so we'll do 1,000. Okay, and now, what about your tunnel? What resistivity of a tunnel would you like? You want it resistive, conductive? Oops. So resistive tunnel. So resistive, how big do you want it? So we can have a radius. Only goes from -40 to 40. So. 'Anybody? 10 meters? Big tunnel? Good? Okay. And depth? Depth to the center? Would you like?
20 meters.
Well, it's depth to the center of 10-meter radius. Let's vary it.
Doug, that's the max it'll go, I think.
Sorry?
The most it's going to go down is 20 meters.
Oops. Oh yeah, so we can only go 20 meters. 20 meters depth. So that's buried as much as we can. Okay? So now we've got that set up. And the first question has to do with, well, are we exciting things, right? So we've got an electrode here. Are we exciting things? So on this row, field, currents, charges. So you see here the currents are coming down, they're getting deflected around this guy. There are some currents that are, okay, you've distorted the fields. If you just wanted to look at, so that's the total currents. If you wanted to look at the primary current, so that's the currents without the target, they look like that. If you wanted to look at the secondary currents, which are the total currents minus that, look like this. So you can see there's kind of almost a dipolar type of secondary currents that they're coming with that. So one of the things that we've been talking about is charge. So if I was to plot the charges that are associated with this, any suggestions about what we might see? Anybody? Charges? So we plot the total charge. We see? Is that what you expected? Why? That's sort of not. So that's a representation of the total charge. So what's happened there? Anybody?
They don't have anywhere to go. That's the only place.
Where are they?
Around.
Around the tunnel?
I don't know.
Nope. Pardon me? Okay, so actually the charges are sitting right at the A and the B electrode. So you've got a current that you're putting into the ground. So that's just like, it's a battery. So you just effectively have a big positive charge here and a big negative charge. So there's a big dynamic range in here. So all the charges are based, most of the charges are there. Now you see that, now you're more what you expect. There's positive charges built up here because you're going from a conductor to resistor, negative charges on this side here. So that's the quantity that you're, that's going to generate your potential signals. I think what's kind of interest at this point is, let's go to a simple experiment. So you can go from a dipole to a pole-dipole and also to a pole-pole. So now we're just going to put a potential electrode at some location and one current electrode. So here we go. Here's our current electrode, and here's our electrode. And by the way, actually I'm going to do two things here. One is that we're going to look at the apparent resistivities as a function of where the electrode, where the potential electrode is. So sitting right here, maybe you can't see it, but with that being a potential electrode, the apparent resistivity is 1100 ohm meters. So that's pretty good. It's the background was 1,000, and this was, I don't know, 100,000. I made it quite resistant. This potential electrode out to here notice that this number here is actually 994, which is less than 1,000 ohm meters. Remember I was talking about overshoots and asking you like, okay, why would you have that? So this is now a resistivity that's less than anything that I've got in the model. And if I move it over as far as I can, this actually drops down to 964. So there's a couple things that are I think are interesting here. One is that we're actually getting a resistivity, apparent resistivity that's less than any resistivity that's there. Hence that overshoot. But now with this diagram, we can also understand why that is. Somebody want to elaborate? Anybody? You guys ate far too much at lunch. Daniel, help them out. I mean, why is it that I'm now getting an apparent resistivity that's actually less than any resistivity that's there?
Well, because it's operating resistivity, so the resistivity and the average resistivity is always like a integrated value.
Right, but this picture actually tells you everything you need to know is actually on this picture. We talked about exciting the object. Okay, so that's done. That builds up the charges. That's the first part. Second part is measuring. When I'm sitting up over here, if the M electrode is sitting up over here, my apparent resistivity is 1,100 ohm meters, which, you know, that's all kind of consistent with this being a resistive body, right? But why is it high like that? It's high because my potential is actually close to these positive charges. So the electric potential has increased. That means the apparent resistivity has increased. Okay. Now watch happens if I go over here. So now I'm sitting over here. The charges haven't changed, right? I'm just measuring differently. So I'm over here. I'm actually closer to these negative charges. Even though those are a little bit weaker than these guys, I'm actually closer to them. So that's causing my potential to decrease. Hence, I'm getting an apparent resistivity that's actually less than 1,000. So it's all in, you know, that whole combination of two things. One is exciting the body, and then the other is measuring. Like, where do you measure? From the point of view of exciting the body, something else that's interesting. So just watch these charges. I'm going to take the A electrode. Here's my source. I'm just going to move it. So you can see how the charges on that body move in accordance with where this electrode is. Because this electrode, the currents come in, and they always, you're going to have these positive charges wherever the currents are coming in, negative charges where they come out. Oh, the other thing is, so suppose that instead of having a resistive body, I have a conductive body, then what's going to happen? Andrew. Who's Andrew?
Do you flip the sign of the charges?
Let's try. So I changed that. So now we're going from a conductor, or from resistor to a conductor. I get negative charges, and then over here I got positive. Okay. So there's a lot of things, there's a whole bunch of things that you can explore with, but you can see how informative like these apps are. And the other thing is that what I want to stress is how to use the app. So you don't use the app by firing it up and just flipping some slider bars. You don't learn anything that way. What you do is you use the app and you set parameters in there with respect to a particular question. And then you ask yourself, okay, if I've set these parameters, what would I expect for the currents? What would I expect for the charges? What would I expect for the data? And you sketch those all out on a piece of paper, or at least in your mind. And then when you've done it, then you press the button, okay? And then two outcomes occur, right? Either you see what you expected to see, in which case you understand, or you don't see what you expected to see, in which case you have something to learn. So that's the way these apps are kind of meant to be used. Okay. Can I minimize that, or should I just kill it? Yeah, so what we're doing, why we're sort of going back and forth here, we're actually live streaming this. So this is all going on to YouTube. Tomorrow will also be there. So if you, for some reason, can't make it tomorrow, then there'll still be, we'll provide a link so that you can, you know, at least see what went on. So you're not completely cut off. I mean, it's much better to be here, of course, but can't. So what did we do this morning? Went through the DC resistivity, fundamentals of induction, and then we did inductive source in the time domain. What I want to do now is do in the frequency, and you're all kind of ready to kind of anticipate what's going on. So in the time domain, we shut it off, and we got some kind of decay. In the frequency domain, we have a harmonic signal, and we're also going to get out a harmonic signal. It's got an amplitude and a phase. I'm going to look at the same vertical magnetic dipole in over half space. And what we're going to see as I look at, if I look at the currents that are on a plane in the Earth, they're again going to be circular, just so. Whether it's time or frequency domain, that doesn't alter. Things are just going to move circularly. So I've got currents that are going to go into and out of the Earth. And that's going to give rise to a magnetic field that I can measure. Just the same as in the time domain, if we look at frequency at a high frequency, then things are going to be induced right very close to the surface of the Earth. And if I look at a lower frequency, they are they further propagate. So again, now in frequency domain, we've got the skin depth quantity. So kind of for bottom line, with the effects of frequency, high frequencies see shallow, low frequencies see deeper. And yeah, both sets of currents give rise to magnetic fields. We're going to be measuring something up here. Again, if we look at the layered Earth, same as we had done before, we're not going to see, we should anticipate that we see the same types of results. And so here was the primary current with just a half space. If we do a resistive layer, we're just not being affected by that. If we have a conductive layer, then we see that there's going to be a lot of currents that are induced. And if it's very conductive, then they barely make it through. So exactly the same as in the time domain. Yeah, and here's your corresponding magnetic fields. So on the sounding curves, that again is the same similar situation as in time domain, but now we have two, right? Because we're partitioning things into a real and imaginary part. So in this case, the imaginary parts in the red, real parts in the black. If we add the resistor in, there is a bit of a difference. It's not like you're totally blind to it. It's factor of 10 difference. There's a bit, but it's not much. Compared to adding a conductor in, where the difference between the dashed and the solid lines is really big. And similarly here. So if we come back to the shielding problem, here's our conductive sphere. Now we're going to put in this resistive layer up there. In DC resistivity, we saw that, okay, that resistivity layer completely hooped us. We couldn't see the sphere. And now if we look at what's going to happen, let's do the buried sphere. So what we've got here is the buried sphere in 500 ohm meter background. And this is what the currents look like. So there's currents that are induced in this top region, but they still make it down to the sphere. So we see the sphere. If we put in a resistive layer, we see that we haven't really altered that. We still see the sphere, and arguably even maybe just a touch better than we did over there. So having that resistive layer actually helped in us seeing the sphere. Okay, so this is, again, that major thing for inductive sources. If you have a resistor, you're basically going to see right through it. Yeah. And here's the curves, the real and the imaginary. So this was just with the the half space, and then also with the resistive layer, and you can see that curves don't change. So what happens with the conductive layer? DC resistivity, we were hooped. What do you think is going to happen here? Going to see through, still be hooped? What? Still be hooped, yeah. So just the same as in time. Can't see through. So in this case here, take this, we put on our conductor, and now all the currents are in that conductor. Don't really see through there. So we're going to be shielded. So with the sphere, without the sphere, here's the currents in the conductor. There's really no change. Okay, so let's do now one case history, another one for groundwater, but a little bit different. Not sure whether you have a lot of saltwater, freshwater interface types of things, or need to discriminate between freshwater and saltwater in Chile, or not. Whether that's a big issue, or whether irrigation is an issue. This is the problem in Australia. It's a region called Bukpurnong. Here it is down in South Australia. This is a river. It's called the Murray River. Goes down through like this, and there's an irrigation area up here, so it's up on a high plateau. And this is the floodplain of the Murray River, and the challenge is that you get a lot of irrigation, so there's a lot of nitrates and salts that get flooded down into here, and that can make its way into the river and also damage the floodplain. So, salt, and so it's a question of, okay, can we remediate against that, and also do we understand how these things are working and how do we monitor them? So what they thought they would do is the following. So they would drill a couple of wells here, and they would pump water out. So this is kind of a cross section. Here you're up on the irrigation region, and so here's the land surface. Here's the river. So you drill a well, and you pump water out, and then you store it up on a reservoir up here, and then that's supposed to evaporate, and then you're just left with salt. So that kind of pulls salt water out here. At the same time, you might inject fresh water in another region in here to try to push the. That was the goal here, is to pump water out here and also to try an experiment where you injected fresh water into here. Prior to doing that injection, they did a traverse across here, measured the electrical conductivity and also the amount of salts. And this diagram here shows the electrical conductivity. So red is very conductive, blue is resistant. Effectively, this is fresh water, and the red is the salt water. They did the experiment for a year, pump out, flush in, and the extent of the fresh water inland here was actually considerable. So this kind of was the result of doing that experiment. So that was fine, but really what they collect data so that they could get some idea about what was happening in this floodplain area. So you're going to try to think about doing an electrical resistivity experiment. The major ticket items here have to do with fresh water and salt water. So saline water is 3 to 5 centimeters or Siemens per meter. Fresh is 0.01 Siemens per meter, so it's quite resistant. So so that was along this transect here. So the survey, so I'm going to do a time domain EM survey and also a frequency domain. So they did the SkyTem, which we analyzed, but they also did this frequency domain system. Here we are. Here's the bird, and it's got coplanar coils. So here's transmitter receiver. That's about 8 meters different, and there's 4 frequencies from 400 to 130,000. And the flight lines are given here in green. So that's the. For a number of reasons. Because what I'd like you to think about, I'm not going to ask you to be explicit, but I just like, well, if you had seen this slide, from that. You got hertz here. You've got curve here. Okay, so you've done your as a check, it's a calibration check, to say, okay, can help consolidate that, right? I mean, first of all, horizontal coplanar data, 2-coil system. When these numbers better signal, okay, so there must be something more conductive down there. So we've got some math. Maps is going to be associated with so the higher frequencies, skim depth rules, don't see as deep. So this is the shallow, this is deeper. We got in phase, quadrature phase. What does that mean? Well, that's just that part. You remember, we just got this current, part of it's in phase with the primary, part of it's out of phase. So now these terms are no longer mysterious or odd. You're quite familiar with them. And yeah, and then I got a sounding curve. It's kind of interesting. So I got a sounding curve. Looks like this. So I got a in phase part that goes up. This is frequency, and quadrature phase that goes down with frequency. So what understanding do we get from that? And then how does that relate to this characteristic thing here that we saw, which was the response curve? So I see something like this, and the first thing that would come to mind is, oh, is there a reconciliation with that, with, let's say, the response curve at a high induction number or a low induction number? Am I dealing with a really big conductor here, or a small conductor? How does all that fit in? Anybody care? Whoops. This is dangerous, isn't it? Sven.
Well, I would say, as you said, low frequencies are more deeper, high frequency are more shallower. We've got changes in conductivities in frequent phases. If you got in phase sounding curve that goes up.
Yeah, okay. So I've got in phase that's going up, and a quadrature phase that's going down. So on here, and this is what I was trying to get at, that's sort of characteristic of a response curve that we're operating over in this region in here, because this is induction number, so that's the same as frequency. So so if I'm on this side, I'm increasing, as my frequency increases, my response goes up, and for the real part, and it goes down for the imaginary. So these curves are exactly kind of what you'd expect from this response curve if you're operating over here. And that was kind of what I was trying to get at. So that kind of everything on here actually makes some kind of sense, or that you've got some idea about what's going on. So now we're going to take those data, we're going to invert them, and we'll do a 1D inversion and have some kind of quasi-static implementation here, so that we don't we keep things fairly smooth. And so here we've got high conductivities coming in here, and our interpretation is going to be that we've got high conductivity, so these would be the salts that are coming in here, and so the river is actually kind of gaining in salts over here on the blue. The water is, fresh water is going out, so the river is kind of losing fresh water. From the point of view of the Australians and CSIRO people, what they were really interested in is kind of how these salts are moving in, and that actually gives them a fair bit of information. So here's the overall situation. You've got irrigation that's going on here. Stuff is flowing into the Murray River, and by going ahead and doing airborne time domain data, you can come up with the conductivity structure and get some idea about how the salts are going. This area is actually a test case for the for Geoscience Australia and CSIRO. So they've flown this again in 2015, and now they can do a time lapse between, see how things were in 2008 and how they are in 2015. I'll show you one small example. This was, we visited Tokyo, and we were doing a presentation there. And I've got a good friend, Yuji Mitsuhata, and he's head of the AIST, which is the sort of a research organization for the government for doing applied geophysics. And I asked him, I said, well, what are you guys doing? And he picks out this brochure. So this is the one that they hand to the general public to tell them what's going on. And in front of this brochure was this picture. I don't know, well, how cool is this, right? Because this has got virtually all of the things that we're sort of interested in from the point of view of the disk, lots of connections. So there's exploration for oil and natural gas. There's a lot of seafloor EM work, so that can be for methane hydrates. Also, there's infiltration of seawater into the ground, so there's trying to find that interface. Putting stuff in the ground, CO2 sequestration, or maybe aquifer storage. So this is something that we'll see a lot more of in the future, and especially as the rain cycles get more problematic, we need to find some way in times of heavy rain to store things, and times of drought, be able to call it up. Radioactive waste disposal. There's hot springs, so there's geothermal reservoirs, mineral deposits, acid mine drainage, and just large general structure. So I thought this one picture kind of resonated with a lot of things that we really want to do here. The example that they had was drawn from the following. They had an earthquake, and then they had a landslide. And the landslide actually covered a couple of cars to a couple of meters deep. And they were worried that people were buried in the cars, and realized like they didn't have really any quick method of just going over and trying to survey things and see if you could find these cars. So what they felt they would do is they'd build a small system on a drone. So here was their system. There's transmitter coils here, receiver coils back here. So it's a coplanar system. It's in the frequency domain. Number of coils, different frequencies. And they're going to tow this thing with a drone. When you do that, one of the first things that you realize is like, wait a minute, the drone is actually giving off a lot of electromagnetic noise, right? So we got to be away from that. They did some tests. If they're 3 meters away from the drone, you get something that looks like this. So it's pretty high noise. If you're 4 meters away, you get the red curve. If you're 5 meters away, you get the blue. So at 5 meters, there's your noise test. You could drag this sensor around. Then you want to detect things. So now you have to kind of go back to these fundamentals. Okay, I've got a primary field that's going to fall off as 1 over r cubed, and I've got a secondary field also falling off as 1 over r cubed. So you need to be cognizant of that, and that also means you need to fly it as close to the ground as possible. Then we're in the frequency domain, so we can have an in phase and a quadrature phase. But in this case, because it's a highly metallic object, you're going to be in that high induction number. So you really only need to consider the in phase. So that's what's plotted here. So here's the trajectory of the drone. You can see how challenging that might be. That's why these kids are probably better geophysics guys. You know, they've grown up. They've got 2 thumbs on a little joystick. Anyway, this is the path of the drone, and then it's plotted. What we've got here is the signal color coded. And so here is the 1 car at 1.5 meters depth, and here it is at 3. Anyway, I show you that. First of all, it's kind of interesting. But secondly, what it does is reinforce the whole concept of scale for electromagnetics. This guy back here, he's the same as the bigger resolve system. And nothing really changes as far as the fundamental physics and data, things like that. So all the basic principles that were learned to make a resolve system, they just get carried right over to here. And then, of course, there's some details that are. Okay. Pardon me?
We could do this tomorrow.
Yeah, I'm thinking that we might have to leave some of these. So I'll tell you what we've got, and then we can, depending on interest, we can do some tomorrow. This is a case history for Helisam data. And basically it's massive sulfide deposits. They're sort of stringer, copper, gold, and zinc rich. So you're trying to find these, and the thing is, these are deep. So these are kilometer deep, and the question is, how can you find that? And what was done was to use this put a large loop on the ground, and then the data you're flying over with a total field magnetometer, and those are your data. And now you want to process those data to get data out that you can actually invert in 3D, and that's what this does. Perhaps the interesting, or one of the interesting takeaway messages with this is that there was a power line in these data that really kind of screws up, especially the early time data. Those early time data are often then thrown away because they're felt that they're contaminated. However, what we were able to show here, and the primary author is Diquan Yang, who was a postdoc with me, was able to show that if instead of throwing away those early time data, you actually take those and try that reproduces that data set, then you can go ahead and eventually work with the full, complete data, and you'll get out a better conductivity model. So that was, I think there's some really interesting things that came out of that. There's another case history that has to do with orogenic gold in Baffin Island region, and it's looking at very highly conducting tabular objects. And so there we use a bit of a hybrid scheme to get kind of a parametric model as well as a voxel model with both frequency and time domain EM, and get pretty good recovery. So for people who are interested in EM for minerals, these turn out to be pretty nice case histories. And then there was a third case history of Magdalena. The interesting thing about this case history is that, again, looking for massive sulfides, but they didn't really know which tool to use. So the initial target was found with airborne time domain EM system. Then they wanted to do something on the ground. They couldn't decide, should I use DC resistivity? Should I use surface TEM, sort of in a TORAM configuration, or in a kind of like a moving loop type of system? And so they experimented with all of these, decided on one, and then went to do the rest of their exploration program with that one technique. And they also included some borehole time domain EM to show that you could find off-hole conductors, and yeah, eventually was really quite successful. I like this particular case history because it's a real careful use of, okay, we've got methodology A, B, C, D. We've got a test area we could work with, and we're going to work with the test area and see which is better, and then adopt that.
Just try getting you back on the call.
Sorry? Okay, so now we'll do is try to put a few things together that we've done this morning. So we started off with DC resistivity, then we went to inductive sources. What we're now going to do is to put them together. Once we get linked back up. Sorry,
If it's messy.
so grounded sources play a big role in electromagnetic geophysics. So any DC resistivity survey, is a grounded source. And we've talked about just using things as a steady state, but you could also think about recording, putting in a time domain waveform through that. It could be harmonic, could be a step off, it could be whatever you like, and actually using that as an inductive and grounded experiment. So what I'm going to do is take you through the basics of that, and we'll look at both effects, both the induction effects as well as the grounded effects. And this, of course, plays the role in all of the seafloor EM, these hydrocarbon exploration programs that are towing large transmitters and receivers. So we're first going to kind of go through a little bit about electric dipoles and put them in hole spaces and look at both conductive and resistive targets, just so that you've got an idea of what's going on. So here's the motivation. Anything that has to do with marine, so that could be for de-risking, it could be for submarine massive sulfides, could be for gas hydrates. Larger problems, perhaps looking at structure of volcanoes. And there's a number of systems that you may have heard of, like LOCAM, HelixAM, GreatCam. All these involve some type of grounded source and looking at both grounded and induced fields. So here's the idea. In DC resistivity, we put a current in, went through there, and we got all the charges built up. And an inductive source, time-varying magnetic fields, we get currents. Now we're going to put them together, and we get currents that are kind of going through like this, but we're also getting time-varying currents in the wire that are going to induce currents in our bodies. Well, first of all, for an electric dipole in a hole space, there's just a couple things to note. One is that the fields fall off as 1 over r cubed. It's a dipole. And yeah, secondly, if we're in a hole space, everything is going to be geometrically similar. So you could imagine. So when I say electric dipole, I just mean like a little piece of wire, and you can imagine a little generator hooked up that. So you can think about it. So we've got a current, and then we're going to turn it off, and then we're going to measure at various times in the uptime. So at early time, 10 to the minus 4 milliseconds, that's pretty early. The diffusion distance given by this, it's about 4 meters depth in here. So what we're looking at here are the current densities. At 10 to the minus 3 seconds, the currents look like this. So what they're doing is they're initially concentrated, and then as we go, they sort of start to decrease in amplitude and spread out. This is about 3 orders of magnitude less. So the yellow here is 3 orders of magnitude less than that. 10 to the minus 2, like that, minus 1. So the takeaway here is if I have a little current element in the Earth and I just let that go, then it's going to just diffuse outwards and downwards. So the amplitude is going to decrease and everything goes away. So that's an important principle. You need to keep that in mind. Every time I got a current in the ground, if I just let it go, it just dies out. Frequency versus time, we'd expect more or less the same thing. The only difference, of course, is that for a frequency domain system, the primary field is always on. So this example is nice. So we're looking at the time domain currents here at 10 to the minus 4 seconds. If we take the reciprocal of that time, then we have a frequency. So 10 to the minus 4 seconds is like 10 to the 4th kilohertz. If we look at the currents at that frequency, they look like this. So 1 diffusion distance in time puts you here, 1 skin depth puts you here. So those things are pretty much the same. At 10 to the minus 3 and a decade later, we get currents that look like this. A little bit later, at 10 kilohertz, looks like this. At 1 kilohertz, it looks like that. So for each of these, all we're doing is, if you had 1 kilohertz, you take the reciprocal, that's 1 millisecond. Okay, and we can see that things are looking pretty similar. So the thing I wanted to really bring home here again, if you have early time and high frequency, if you just take the reciprocal of one versus the other and try to kind of get some idea of, like if you got something in frequency at a particular frequency, if you did 1 over that frequency and looked at what the time domain response is, you wouldn't be that far wrong. So the currents would be more or less the same. And so late times and low frequencies are about the same. And then the two quantities, diffusion distance and skin depth, kind of pertain to both of them. So again, just trying to get rid of all of this, dichotomy between time and frequency domain. Okay, so now we'd like to look at this grounded dipole. I'm going to take a wire, put a generator on here, and we're going to put the current into the ground. The wire could be straight or it could be made out in a horseshoe. And as I say, the problems are extensive. They can be used in a whole bunch of different ways. We can have different frequencies or times and geometries, all the stuff that's usual. But what I want to do is take a simple example and just see if we can work our way through. So here's where we are. We've got a system. Here's steady state. So I have a generator up here. So we put current in here. Current goes back through here and around like that. So a steady state, we've got currents in the ground. And now what we're going to do is shut it off. Okay? So we're going to shut this off, and we're going to try to anticipate, okay, what is going to happen. So let's take it apart. So first of all, let's just think about the wire. Okay, we've got a wire, and we've got a current going through it, and now I turn it off. So what's going to happen the moment that I turn that off?
the electrons in the wire want to move.
Right? Yeah, so there's nothing in the wire. I turn the wire off, there's nothing happening in the wire. What happens outside the wire?
Well, you should expect to see some secondary currents in the ground. As long as you stop the.
That's right. So we've got,
Yeah.
we're changing the magnetic field. Okay, so we used to have a current in the wire, now we get rid of that. So for the Earth, there's been time varying magnetic fields. So we should see some currents in here. What are those currents going to look like?
Should be opposite on the direction of the field that you are using with your wire. You also can expect to have some eddy currents in the circuit.
Okay, so the currents, so the moment I shut it off, then the currents then go in the other direction. And okay, anybody else? Valentina.
What's next?
Yeah, what are they, what's going to happen? I'm going to turn the currents off in the wire. What's going to happen? So,
Appears a magnetic field during the transient current.
yeah, there's going to be a time varying magnetic field, exactly. That's going to induce currents in the Earth. Yeah.
I guess that we're going to see some change in the space that is affected by the kind signal of one of the currents, and it's going to, like, move or go away from the.
What do you think is going to happen immediately after I turn the current off?
Maybe an overlap of currents
Overlap of which currents?
between the ground currents and the initial state of the other the current induced by the.
Okay. Yeah. Yeah, so we're not going to worry about the currents in the ground. We're just going to worry like, okay, I've got a wire, okay, and now I'm just going to turn that wire. I've got to turn the wire. I'm just turning it off. Well, something's got to happen. There's got to be a consequence. And
The magnetic field is robbing, so there's a variation of the magnetic field. So there are electric fields that are built.
right? Absolutely. But can anybody? Yeah, like any idea of what the currents would look like?
Magnetic field induces a new current.
Yes. So what would the currents look like?
Like circular.
Circular? No.
Opposite sign.
Opposite. Oh, that's what Hector was saying.
Like the transmitter?
Pardon me?
Like the transmitter.
The currents in the ground are like the transmitter current.
Well, the other one was round, this one's along the line.
And which way is it going?
One to the other one.
Okay. So the moment that I turn that current off in the wire, okay, now there's a response in the Earth because there's a time varying magnetic field, right? So that's going to generate currents. How are those currents going to look like? Well, they are going to be generated in a way that opposes any change. The Earth likes to stay constant. It likes flux to remain constant, right? Just the same as we were working this morning with plates, and that helped us decide about the currents. So that means that if if I'm the current wire here, okay, and I turn my current off, if you're not going to be affected, the only way that can happen is if there's another current, a replacement current, a current that's going in the earth that looks exactly like the current from the wire. So that's the ticket. I turn the current in the wire off, and immediately there's a real current that's in the ground that's traveling along this way. So it travels this way, not the other way, because it has to keep, for point here, it has to keep the flux constant. So there's this transference of a current in the wire immediately to the current in the ground, and now we know what happens, right? So now I got a current in the ground, I know what's going to happen, right? Because we just went through the ground like a dipole. So it's going to look like this. So turn it off. I get a current here, then it just diffuses. Now I got in current, just sort of diffuses down. Okay? What about this stuff here? The moment I turn that generator off, what happens to those currents?
They have inertia.
Yeah, I'm not sure what that means. Inertia?
The moving charges are still with velocity, so they will keep moving on for a little while.
Keep diffusing?
Yeah, though you might both be saying, but now for any of these, that's just like a little current filament, right? We saw that if I have a little current filament and I just let it go, so every little current element is just going to go swish, swish. It's going to diffuse out. So the grounded currents, the moment that I take that forcing function off, are just going to diffuse out. Let's take a look. Let's look numerically. So here's a half space. So that's plan view. This is cross-section. Let's concentrate on cross-section. So I got an A electrode here, B electrode here, goes around like that. Okay. At early time, at 0.02 milliseconds, okay, I'm looking to see what happens, and you can see what's happened. Here's all the currents. They're just right underneath that current wire. A little bit later, they look down like this. Later. So again, these color scales, the yellow is not always the same amplitude. You can see exactly what happens. That the wire, the current from that wire just kind of diffuses out. Okay? So wires turn out to be really important in electromagnetics. So now let's do one more step. Let's do it with a target. So suppose I got a wire and I got a target. This is a buried conductor. Okay? I want to see if I can find this guy. So I'm thinking, well, DC resistivity, that kind of works, right? So if I think about it from a view of coupling, from DC resistivity of A electrode here, get negative charges here, positive here, okay, I should be good to go. How about from an inductive viewpoint? If I have a wire that's across here, now my magnetic field is coming in like this, so that's perfectly coupled, right? So if I have a changing magnetic field, I can imagine I can get currents here, should be good to go. So it would seem, just from the outset, this really should be a good example to use. So let's take a look at that. Here I've got the current lines, and you can tell actually by looking at those, right, as to whether that's a conductor or resistor. You can tell, oh, it's a conductor. Look, they're being sucked in. It's good. Now look what, so this is just before stage. Now look immediately what happens the moment, or just shortly after I turn that system off. Those are the currents. They're doing kind of what you think. First of all, they're maximum towards the top, okay, because that's the energy is still diffusing now. But look at the shape. Those are circular currents. So those are the vortex currents that we're thinking about, right? Now what happens with time? As time goes on, these currents diffuse inwards. There's still vortex currents that are there. Later, they become more uniform, and then they're gradually dying out. And then later, it looks like this. These are the lines of current. The lines of currents are flowing through this way. So there's a lot of stuff that's going on here, right? So, we start off with galvanic currents, and then the moment we turn things off, the induction takes over, makes these vortex currents, and then we end up with just this broad diffusion of currents coming here through the galvanic part. So that's what this looks like. So we got galvanic currents, early times got vortex currents, and at the end we have back to galvanic currents. So it's not a trivial process. Definitely not trivial. Oh, okay. So now everybody's working for BHP or GRS here. I'm not sure who else we got, but everybody's tight on money. Even in good times, Terry is known to be just a little cautious, doling it out. So we know a lot of stuff now, right? We know. We're kind of getting an idea of what's going on, right? We've got the currents. We know how the currents are flowing. We got some concepts of charges, right, being built up. So we should be able to estimate, okay, which fields do I want to measure? So you have a limited budget. You can only go out and measure a couple of fields. I mean, it's an ideal case, right? I suppose we know exactly where this thing is. Which fields are going to give us the most information? Well, first of all, which fields could we measure? What do we have at our disposal? What fields could we measure? Pardon me? We measure electric and magnetic fields, right? And these are all fields, so they have components. So let's take electric field. Let's suppose that this is the X direction, and into the board is the Y. So which component of the electric field is going to be most sensitive here? X. So see the charges that are built up here, right? So that means the X. So the currents are going here. So the currents are like this, right? So that means that they're in the X direction. So if I measured EX, that looks like that would be a really good thing to do. Let's see. So here's the EX field. So this is the half space response at different times. And here's what you get with the conductor. So that's significantly different. But look at 1 millisecond. I mean, it's hugely different. And at 10 milliseconds, it's really big. So the electric field in the X direction is a really good thing to do. Okay? How about magnetic field?
Magnetic field should be stronger in the Y.
Good. Right, so we've got currents that are going like this, right? And so that means that the magnetic fields from them, are like that. So they're coming right out of the board, right over the wire. They're coming right out of the board. That means that it's the Y component. The other thing, notice if we went offline, off the wire, then over here the magnetic field is coming up, over here it's going down. So there might be some use for measuring the Z field, vertical field of the magnetic field. So here's Vy, and look at this. So here's the half space, here's with the conductor, and at 1 millisecond especially, it's hugely, 10 milliseconds also is really big. So Ex, By, in this case, those would be your choices. If you did Bz, you'll also find significant information, provided you go offline. And so you get this kind of change versus that. Okay. Good, so that's a conductor. So that's actually quite a bit, right? So we just think about, okay, I got a wire, I got an object, I can kind of think about, you know, the DC currents going through, I can think about inductive currents through, I've got an idea of which fields to measure, not bad check for a conductor. What happens if we have a resistor? Christian. Is there any questions? Isora? Isora? ISOR? You guys? I see. Okay, Francisco. Who's Francisco?
I know my students are laughing. I'm not really asking questions. I'm not really answering.
What's going to happen when we have a resistor?
Not going to be much change. The higher value of the fields would be outside.
Okay, so it's saying, I mean, we've got a big contrast, so it'll be the same kind of thing that we had before. Ariel? Who's Ariel? Ah! Hiding behind Lindsay there. Nice try. Yeah, good that. Busted. Okay. Resistor? Think back to the fundamentals, okay? So when we're doing time and frequency, induction, right? And we had difference between conductors and resistors. What did we see? What was the basic thing with induction processes with a resistor versus a conductor?
Is that in the X we're going to have more contrast than in the Y? That makes any sense.
Oh no, I see where you're coming from, because we had talked before for the DC problem, we had a bigger response for a resistor. Okay, good enough. So does that mean it's going to be pretty much the same as what we had back here, or not? Manuel?
I guess that I expect more response in the medium than in the body, the resistor body.
I'm sorry, I mean, you expect more response, what?
In the medium, more than in the resistor body.
The background.
Right, in the background.
So from the point of view of comparing like the fields that we get with from a resistor or a conductor, how are they going to change? Or how would the currents change? Any? I have to call the big guns in here to help them out. Okay. The fundamental thing that we did in before we got here, when we were talking about inductive sources, is that there's basically no currents that are generated in a resistor, right? So a time-varying magnetic field generates an electric field everywhere, unquestionably. However, the currents are the product of the conductivity times the electric field. If you have a very low conductivity, then you have no currents. That's the bottom line. Okay, so now let's see what happens. So look what happens here. Now I'm putting in a resistor. I can tell I got a resistor here, right? Because the currents are going around. Here we are at some early state. So the currents from the wire are diffusing through. But look what's happening in here. There's nothing happening. When we had the conductor, we had these vortex currents here, right? Now we don't. A little bit later, looks like that. Later, looks like that. These are all just galvanic currents. These are just your primary field that's moving through. Get currents through here. There's nothing circulating. It's all charges. So with a resistor, at early times, you just get these galvanic currents. At late times, you get galvanic currents. That's it. Okay, so given that, which fields now do you want to measure? Pardon me?
I mean, the secondary field will not, the magnetic field will not give you much.
Right. So the electric field should still be good, right? Because that's the DC problem. Okay, and it is. Look at 1 millisecond, those differences of 10 milliseconds out. If we look at the magnetic field, it's not very much. I mean, there's a little bit of signal there, but really, there's not very much. So here's the half space, here's the resistor. That's Y and Z. Yeah, you're hard pressed. You know, at this level to pick out anything. Definitely, if you have high quality data and stuff like that, you can pick out something, but there's not much there. So that is the summary. If you've got a conductor, here's the half space. So you've got a conductor, EX, it's good, BY, BZ. If you have a resistor, you've got EX and not so much BY, BZ. Well, now I've started to make things more complicated. I don't know if you want to do this. You make coffee, whatever. So if you're thinking about thin plates, you know, you've got some conceptual ideas about how they. This looks like it would be a good kind of coupling, right? So we still get stuff going in here, and then we get something coming up here. So that looks like it's coupled pretty good. This one, you know, DC resistivity maybe doesn't couple quite as nicely, and EM certainly couples poorly, just sort of in principle. So you can see that, okay, the geometry of the body and the coupling is going to be important. Which also means now, if you're going to try to find something, you want to make sure that you're exciting that object from a couple of different directions. Just to go out and do one direction is a bit risky unless you know kind of what's there. So generally, as a rule of thumb, you know, at least 2 different directions is good. But you know, beyond that, I mean, at some point you can see that, okay, we worked hard enough just with a simple cube. If we're going to go to things that are much more complicated, we just have to appeal to numerical simulations. I mean, it's just too complicated, and especially when you've got things like vortex currents overcoming, you know, getting larger than galvanic and vice versa. It's challenging. So let's do a case history. This is, how many people have heard of the Deccan traps? Okay, and in what context? Why?
Massive flood results associated maybe with a mass extinction event. If you want to go there.
Okay. Do you know anything about them, like how long they went on for, or about what time? What?
Well, they're KT boundary, and don't know how long they went on, but they're pretty thick and extensive.
Anybody else got additional information about them? Yeah, so they were massive, massive flood basalts, millions of cubic kilometers. And, here's India. So these are areas of India that just got covered by this stuff. And, you're talking, hundreds of meters to kilometers thickness of this. The reason that they're potentially associated with mass extinction is that, coming up with all of this basaltic lava, there's all kinds of gases, right? And so that could greatly change the climate. And that all happened around, 65 plus minus million years ago. And so for many years, it was thought that this might be either the cause for the extinction of the dinosaurs or kind of related to, maybe it challenged the habitat, the Earth habitat for things. I think the meteorite impact at Chicxulub in the Yucatan Peninsula is now regarded as the cause for the extinction. But whether it was that there was some marginalization that went on before this or not, we don't know. So this was promoted actually by the hydrocarbon industry because there would have been a lot of sediments, and these basalts may have covered the sediments. And then the question is, okay, maybe there's hydrocarbons underneath. There was a survey that was done. It was a DC resistivity survey, went across here. They ended up with a structure that looked like this. With this top region was basalt, so that's about 1.5 kilometers thick, and then sediments underneath, and then the basement. That was sort of general. They believed at that time that the sediments were going to increase in thickness as you went from north to south. And that, however, they just didn't know enough, and they just weren't really sure about this presentation. So they wanted to do something else. And so they decided to do a time domain EM experiment. This is LOTEM, which stands for long offset TEM. The transmitter is usually 1 or 2 kilometers long, so it's sitting out here. And then the data were recorded anywhere from maybe 2 to 15 kilometers away. Each data site recorded multiple components of the electric field and the magnetic field. So that's what the general layout was, and these are the lines that it had. So each of these were lines that were done. Before you do any survey, you should do a proper survey design to see, first of all, ask your question of what it is that you're looking for, and then to see if you can find it. In their case, they were looking for a stratigraphic column that would have basalts at the surface, and they might be, maybe 150 ohm meters thick, but they might be 1.5 kilometers, or they might be 3 kilometers thick. And the question is, okay, if that was true, could you distinguish them? So basically, it's basalts, sediments, which were 20 ohm meters, and then basement, which is 1,000. That's sort of their estimated model, generic model. So then they wanted to see, well, if I varied the thickness of the basalt, do I see any change in the data? So that's a kind of sensitivity analysis. And when you do that, you get apparent resistivity curves that look like this. So they're changing. You're sensitive to the thickness of that basalt. The other thing had to do with, okay, if you specified everything but the conduct or the resistivity of the sediments, if that changed like 20, 50, 100, could you see that with these data? And again, the apparent resistivities are different for each of those, and that would indicate that you have some sensitivity. So that's pretty crude, but this was also done a long time ago. But still, it shows the procedure, right? You're asking questions, you forward model, see if you can see some difference. If you can, then if you've asked the right question, you're kind of good to go. So the processing here was basically a 1D inversion. So here is line L along here. And along that line, we have an upper region of basalts from 80 to 140 ohm meters. That's a little bit more than a kilometer thick. And then this dashed line or grayed out zone here is sediments. That's a low resistivity, 16 ohm meters. And then bottom is 3,000. So this showed a thickness of sediments there, sort of about a kilometer. If you go down to G, and you hear, and the thickness of the sediments has decreased. And if you go to K, the sediments are gone. So this is exactly opposite to what they had thought previously. So a fairly simple time domain EM survey providing kind of gross information about what's going on and completely at odds with what had previously been thought. In electrical methods, it's not really the conductivity that is so important as far as determining what an object is, but it's really the conductivity thickness product. In other words, if I took two plates and they each had the same conductivity thickness product, then they would give the same EM response. So what they're interested in here is looking at this conductivity thickness product, which is called the conductance. So it's the conductance that's important. And they plotted out the regions that had worked on before, and they found that this was a region here of high conductance. That means you should be most sediments there. So that prompted them to drill. And here's what they had previously thought. There should be basalt up to this level here, which is about 1,500 meters. Then the layer of sediments, that's about a couple of kilometers, and then basalt underneath. So they drilled. Here's the geologic log that came from that. And in fact, this region up in here were listed as Deccan trap basalts. All of these guys here are sediments, and underneath are basalts. So, you know, a crude, at least by today's standards, data acquisition and inversion, but actually captured the bulk of the information, and it turned out to be extremely useful. See what? Yeah, go ahead. Pardon?
Oh, sorry.
Oh, I think stretching. We should all stretch. How many people here are interested in the marine CSEM problem and its application to de-risking?
Well, I've already seen Steve's talks, that's it.
Okay. Okay, so here's this. I think you'll find quite interesting. There's a couple of reasons for showing this. The general marine EM problem is as follows, that we've got applications, oil and gas, submarine massive sulfides. This is something that I think you're going to hear a lot more about in the next couple of years, because remember there's all these ocean ridges, there's these black smokers that are coming out, they're depositing high concentrations of metals sitting right at the surface of the seafloor, and if they can be delineated, they can actually be mined fairly readily. So the Japanese will probably be starting this within the next, probably year or so. Also methane hydrates. Not sure, is there interest in Chile in methane hydrates?
Not yet, but should be, you know, we have so much ocean.
Yeah, that's kind of what I thought too. I've got a diagram later on though. Help characterize it. There's tectonic studies. For some places, offshore unexploded ordnance are important. And also offshore groundwater. I know, especially in the Mediterranean, people are really interested in freshwater aquifers extending underneath the some saline water in the oceans and some overlap. So there's lots of kind of interesting problems that go along with that, and that means that you need to acquire data in the ocean. The basic things, I think, for most things is that seawater has a very, well, it's a very low resistivity. It's sort of a high conductivity, and freshwater is really resistive. So we've already kind of seen that. Sediments are maybe 1 to 5 ohm meters. Hydrocarbons are about 100. Gas hydrates are a couple of thousand. Depends on temperature. And massive sulfides are very, very low resistivity. So those are usually the things that are really of most interest, and that kind of sets up the, sort of sets up the problem. When seafloor EM first came into play, well, about a decade and a half ago, the question was really as follows. We've got ocean, and we've got sediment, and then maybe if there's a hydrocarbon layer here, it should be really resistive. So the question is, can you see a resistor inside this, this basement? From the work that we've already done this morning, okay, and talking about inductive sources and galvanic sources, you're trying to find a resistor. So what kind of a survey would you choose? Would you try to use something that's, you know, it's got a strong induction component or a strong just galvanic type DC component? Basics? Brendan? Who's Brendan?
That's me. I wasn't paying attention.
Busted! That's why having a name list is really good. Because nobody knows whose name it's going to be. Okay, so the question is, you're faced with this. And this is a like really serious question, right? So you want to try to find a resistive hydrocarbon layer at depth. Okay? What technique do you use?
So from before, the inductive technique would be difficult for us.
Okay, so we should not use the inductive technique. Anybody else?
Conventional resistivity, dipole, ground dipoles, ground.
Right. Okay, so we've already decided that inductive sources are not really great for finding resistive targets, right? So the very first thing that you think about if somebody says, okay, I'm looking for, you know, a resistive target, is like, okay, probably not an active source, although that's a bit dramatic. But your first choice would be, okay, can we make a galvanic source work? Okay, so let's see if we can make a galvanic source work. So what we do, well, we need a transmitter. That's, I can tow a long wire. So I have a generator, have a wire, so that gives me a dipole. And now if I measured the electric field at places along here, then I'd have basically a DC resistivity experiment, not one that's right down our surface, but I'd have one down there. Okay, so what are we up against here? Suppose that this thickness here is a kilometer. Okay, if we're going to try to find something that's a kilometer deep, then how far out do we want to expand our array so that we're going to see that? Yeah, sort of a factor of 3. That's good. So that would be 3 kilometers. In fact, in a lot of these cases, this depth is more like a couple of kilometers or 2.5. So that Barents Sea example that we just stopped over was over 2 kilometers depth, and that meant that they actually had just about 8 kilometers of cable going out. These are huge experiments, right? You're on a ship and you're putting out cables that got receivers that are 8 kilometers out there. So the thing is, okay, whether or not you can see this guy. So here was the type of transmitter. So you're just pulling it. So here's your generator, and here's your electrodes. And now you're going to tow this guy over along your target, and you're going to see if you can see something. So here is the background resistivity that doesn't have a hydrocarbon layer in. So we've got the air, we've got the ocean, and we've got the sediment. And if we did this experiment, we'd end up with an electric field curve that looks like this. Okay. It's sort of going down, and it's got this little bit of a kink here. If we put the hydrocarbon layer in, we actually see something that looks like that. So there's your forward modeling survey design. No question, if you actually had that hydrocarbon layer there, you've got significant signal here, you'd be able to see that. One of the things that perplexed people for the first couple of years, and there was a lot of talks given, there was a lot of research that was done, was how the energy actually travels. Because there was something called the air wave that seems to come in early enough that obscures the signal that you're really looking for at long offsets. And how can the energy travel? It can go through the ocean, okay? It could go through the sediments. It could go down to the hydrocarbon layer and then up, or it could go up to the ocean, or up the ocean to the air, and then over and then back down. And this was called the air wave. A lot of people couldn't quite figure out what was going on with that. And there was a lot of controversy. There was a very good paper that was written by Peter Weidelt, I think in 2007 or 8, and that outlined mathematically what was happening. And he showed asymptotically that you got these various waves. What I'm going to show you now is a movie that within 20 seconds of watching this movie, you will understand completely how this energy is traveling, and you'll be wondering, why were people having this questioning about the air wave and how it fits in. And I think what this does is it shows also the power of visualization and numerical computing, the ability to compute something and dynamically watch wave fronts and see how they propagate. So I'll show you that. So what you're going to see is a movie of the following. So there's going to be a source that's given off here. And so it's a time domain source. Actually, here's the other thing. The data are acquired here in the frequency domain. So they're working with frequency domain EM and using it, 0.5 hertz, 0.1 hertz, ... right? So, and then the simulations are done in the frequency, and then you're plotting things up in the frequency domain. Okay, that's fine. But when you look at the frequency domain plots, they're actually pretty hard to make sense of, because you've got always this primary, and you've got this splitting between the in phase and the quadrature phase. And honestly, goodness, you can look at these things and you can be scratching your head as like, okay, I'm not really sure what's going on. The intuition, however, for understanding electromagnetics comes from the time domain. And that's where this movie is going to be, because this movie is going to show time stepping in the time domain. And with that, you can see the wave fronts. And once you see the wave fronts, it's like, well, how simple is that? And we can also put into account a lot of our sort of fundamentals that we did earlier. So, okay, so what we've done, we had a current in there in the transfer, we turned it off, and we're watching the energy propagate. And look already what we can see. So first of all, this is ocean, so it's high conductivity compared to this, which means that it diffuses more slowly. So in a conductor, the waves travel more slowly. And we can see that. So in here, it has diffused out this distance. In here, it's actually diffused out that distance. Okay? So the fact that this is more resistant than that means it diffuses faster. Okay? So already something that we've learned today can be used to understand this picture. Now, what I want to have you watch is that as this energy gets down to this layer, this is a very resistive layer. That's your hydrocarbon. And the energy is going to come down here, and then now it's going to diffuse really quickly because it's resistant, and it's going to go zipping along here. So it's like a guided wave. See that? Look at that. So the energy comes down, hits this region of resistance, and just zips through here. And while he's zipping through, there's going to be energy propagating up into any receiver that's here. Now watch what happens here. So this guy, he's been slow because he's traveling through the ocean. He's just kind of getting up there, and he's going to hit this interface. Here's the air. Here's the water. But here the air is really resistant. And you're going to have to look real quickly, because once that energy hits, it's going to go zipping along. And it's dead. Just zip. It's gone. So the thing about this and watching stuff in the time domain really helps sets the physical understanding of what's going on. Once you understand that image, then you can go back to the frequency domain and you can kind of help unravel things. But if you're just first given the stuff in the frequency domain, I think it's a little bit hard to really kind of figure out what's going on. So yeah, that was the purpose of this thing. I'll just try it once more. So the two head waves. And eventually, so if you're sitting here, okay, so there was initially stuff that's coming along here and going up. But you can imagine if you go out far enough, this is propagating along here at a fast compared to here, but still slow compared to here. So you can actually get energy that propagates out this way fast enough, overtakes this, comes down, and is actually the first arrival at your receiver. And that is actually what caused that kink in that first image that I showed you. Okay, so that's probably a good place to leave it for coffee, since the coffee's there.
Oh, thank you.
I guess we can ask people who aren't going to be here. I see people who aren't coming they can still be.
So we can do like the PM.
Yeah,
We could do, or we could jump right here, or we could actually jump straight to IP. Depending on what is most interesting. Whatever we will cover.
Yeah.
Sí, pero hay que esperar a las 4 de y salimos mañana.
I just thought they'd be so much more interesting.
Yeah. I feel like sharing the synthesis makes it probably hard.
We don't have.
Right, but we could probably.
No, eso es lo que me dijo el Marcelo.
You turn it down.
Because in some ways that provides a little bit of closure on the so you can revisit to see.
You know.
Okay.
Because there was just half a dozen.
But it seems like MT is highly of interest. To get a local example, I think that all sort of bodes well. The internet is really
Ya, sí, verdad. Por eso no lo sé. No sé qué está leyendo. ¿Usted hizo eso?
Yeah. Okay, actually, I think that's, we have plenty. Yeah.
And I need a picture of you and Daniel.
Oh.
It's pretty outside, actually. Like that.
I don't think you are.
It's not into stack together.
No, you were asking me about I told you that's what will happen. Somebody will tell you the day before.
That's easy.
Just give me the money.
Just ask for the license message.
Yeah.
No tengo que
No, pero lo que pasa es que no. That's like, yeah. Like, waiting. Yeah, yeah. I mean, some of it, I did it. So when I'm Yeah. Yeah. When I was just trying to work out how to tell the people in there in Spanish when there was Twitter.
There we go.
¿Quién hace las fotos afuera, hombre? Sí.
Nunca te digo.
So Joan is very proudly sent me.
Oh, everybody is
Joan was very proudly sent me a photo of our bedside lights that he put up today.
I prefer the one that comes with the machine.
Really pretty cool. These are the ones from Easy that I wanted him to pick. So he went back and got one. They're pretty good, yeah, they look nice. Really something closer for
Those are pretty good. Give it a go.
I just buy these for a little bit accessible. No, he sent me a picture, and conveniently, the robots have labels in it. Yeah, that's able to confirm. That's,
We got a little spice on this.
it's like with us, we have chaos, doesn't What do you think he's moved It's quite fun, actually. Yeah, exactly. I just have to make sure you start with necessity
So there's a number of people who won't be here tomorrow. So we're trying to figure out how we can kind of juggle things. Also, I'm still having a little bit of difficulty knowing how much emphasis to kind of put on mineral exploration and associated things with that. But what we've decided to do is follows. We'll present, we'll do the natural sources, just so people can, for those people who are leaving, they'll at least have some spectrum of natural sources. And we'll do one case history on Santa Cecilia, which uses not only magnetotellurics, but also DC resistivity and CSAMT for mineral deposit in Chile. So hopefully that kind of resonates with people. And then that probably will then be all we'll do for today. And then tomorrow we can pick it up. And I guess what I'd ask is that people who, if there's particular case histories or particular things that we've just not really been able to get to, if you can let us know, then we can easily incorporate them. But for now, for the afternoon, I think let's do something that could be the greatest benefit to a lot of people. We'll do natural sources MT and then mineral deposit Santa Cecilia. So we've looked at control sources, frequency, time domain. And now what I want to do is to concentrate on magnetotellurics, or natural sources. And the motivation for this is really scale. So we've got volcanoes, we've got base of the salt structures, we've got geothermal energy, we've got groundwater, large-scale mineral deposits like porphyry deposits, and we've got tectonic settings. So all of these things are big, and we're going to excite them. We need to get big energy to go into the ground. The question is, how do we do that? And what are we up against? For a control source, if we use a loop, then remember the magnetic moment was the current times the area, and we lose 1 over r cubed geometric attenuation this way, and 1 over r cubed back. So that's 1 over r to the 6th. So that's a total geometric decay of 1 over r to the 6th, which is really a big number. Things fall off very, very quickly. What we'd really like to do is to get rid at least of this geometric decay. And we could do that by imagining, let's suppose we had a really, really big current loop, say 100 kilometers by 100 kilometers. And then the field in the middle of that loop would be basically a plane wave that's coming down. And then we don't have a total geometric decay of 1 over r cubed. So that would be good. Unfortunately, we can't do that, right? It's kind of hard. But we do have the benefit. Mother Nature provides some potential solutions here. Here's an image, not to scale. There is the sun. Here's the Earth. Here's the Earth's magnetic field. Here's our magnetosphere. And you can see how the solar wind, the particles coming up from the sun, just kind of make this magnetic field into kind of a tear-shaped trajectory. The sun emits solar particles. I'll show you in a moment a movie. Charged particles that come along, and then they basically get funneled into the Earth's field lines, and then they come down into the auroral ovals, both in the northern and southern hemisphere, and they give aurora. But I'm not sure, is anybody here seen aurora before? Oh, not bad. That's a good one. Yeah, that's not bad for me. The other natural source is lightning. So I'm going to show you a movie. What's going to happen here is there's going to be a solar storm, solar flare up here. It's going to spew out a whole bunch of particles towards the Earth. Those particles are going to interact with the Earth's magnetic field. They're going to kind of go around. They're going to go around here. And then there's a very intriguing process called field line reconnection, where the particles are going to get trapped in, and then they're going to come back along field lines, and then they're eventually going to spiral in along the field lines. So that's what the movie is going to show. Yeah, so there's the eruption. There's the particles coming out. Sometime later, and here's the field line reconnection. Yeah, and then they continue to come in. So as you're sitting on the Earth, you're seeing these particles come in, and it's just these shimmering waves of light. It's immensely beautiful. It's really breathtaking. So that's solar storms. We also have lightning strikes, which is one of the larger components of our field. So if we have a lightning strike, that's just movement of charges from cloud to the surface of the Earth. And that gives rise to time-varying current, and those magnetic fields propagate up, and they hit what's called the ionosphere, which is a region about 100 to 500 kilometers up, and that's a very conductive region. So an electromagnetic wave that propagates up into that will get reflected back down, hits the Earth, Earth's conductor, so it gets reflected back up. So the bottom line, it just kind of gets reflected around this cavity here, our atmosphere, is basically a waveguide. So there's a lightning strike towards the equator, and you can see it in northern or perhaps even central Chile. So that's those are the energy sources. The overall electromagnetic energy spectrum looks like this. This is period. So that's 10 to the 5 seconds. That's 10 to the minus 3 seconds. So there's 8 orders of magnitude there. There is a region in here, it's called the dead band, that there's a deficit of signal that can be challenging to collect really good field data in that region. We talked about waves, talked about plane waves. So any wave that we have when it's impinging upon the interface, some of it reflects, some of it refracts. So it doesn't matter if it's a light wave, a sound wave, electromagnetic wave, a seismic wave, they're all the same. You have a wave coming in, angle of incidence, angle of transmission, and that angle depends upon the physical properties. We had this wave, introduced this wave number earlier on, K. For our quasi-static case, we had that. And here's the relationship between the incident angle and the transmitted angle. And for all of the physical properties that you have that characterize the Earth, it turns out that the transmitted angle here is really such that everything is traveling almost vertically down. So the angle of incidence could be anything, even 89 degrees, something coming in at almost horizontal, hits the Earth and it just gets traveling straight down. That's why when people talk about magnetic tellurics, they often say, I just got a vertically propagating plane wave coming down. But it's because everything that hits the Earth's surface propagates right down. This kind of refreshes some of the things that we did. Skin depth. So different higher frequencies get attenuated more quickly. Lower frequencies travel deeper. Irrespective, you only see a portion of a wavelength. So the difference between control source and natural source. In control source, we know everything. Okay? We know where the loop is. We know what the source field is, waveform in the loop, and we know the boundary conditions. Natural sources, unfortunately, they're random, like lightning strikes. So they're random in space, they're random in time. Some are coming from the ionosphere, some are, it's just a mishmash. So that makes it tough, like trying to figure out how everything is coming in. So that's the big difference. The good news is that Maxwell's equations, when written like this, the electric and the magnetic fields depend the same way on the sources. So if I have a source here, then E and H behave in one particular case. If I have a source over there, then E and H still behave in a relatively similar manner. So it's kind of like if you thought about E and H both depending upon a source. If instead of working with fields individually, you took a ratio of E over H, then that would somehow cancel out the effects of this source. It's not quite a ratio, it's called a transfer function. And what it does, it relates the electric fields at some point to the magnetic field. It's a two-dimensional tensor, and it's got these components, and it says that, okay, at some particular point, the electric field in the x direction depends a certain amount on the hx component and a certain amount on the hy component. So it's just a relationship between the fields. But clearly that relationship involves the electrical conductivity of the Earth. And so the data that are usually used in magnetotellurics are these impedances. A standard MT station is one in which you measure the horizontal electric field components and the 3 components of the magnetic field. And actually, often a remote reference to help in noise cancellation. Talk just briefly about that in a second. So when you've got plane waves on a homogeneous medium, there's actually 2 kinds of ways in which the waves interact with the Earth. There's something called the TE mode, in which the electric field is parallel to an interface. So here's the Earth, here's the air. The electric field is parallel to the interface. The magnetic field is this way, and that's called the TE mode, transverse electric. You can also have transverse magnetic, in which the H field is parallel, but now the E field is crossing. If the medium is homogeneous, then this impedance just becomes EX upon HY, and the impedance to a resistivity with this formula here. So this is the sort of the prime formula of magnetotellurics. If you use values, complex numbers, and you square them, and you divide by that, you actually get the resistivity. The phase also can be evaluated, and for a homogeneous half phase, it's pi by 4. So MT soundings in 1D are kind of behave just like you'd hope. So we've got, and let's suppose we've got an Earth structure, 100 ohm meters, 10 ohm meters, 500 ohm meters, right? If we work, first of all, with really high frequencies, our skin depth is confined to this. The apparent resistivity is 100 ohm meters, which is great. As the frequency decreases, you're starting to see more of this layer, and the apparent resistivity drops. As it goes down further, then you're sampling more of this 500 ohm meters, and the apparent resistivity climbs up and would eventually asymptote to 500 ohm meters. So this is great. This curve actually sort of reflects what's happening in a 1D Earth, and then the phase is also informative. So in 1D, this impedance tensor has really got 2 off-diagonal elements, but they're both the same, because if it's 1D Earth, like I can't tell the difference between here, right? So if this is EX, that's HY, it's going to be the same here. So these 2 guys are the same, and so there's really only one number. We have an app that allows you to simulate what the impedances are and what the fields are like as you go down into the Earth. And not only can you change conductivity, but you can also change mu and epsilon. So in 2D, things get a little bit more complicated. The general impedance sensor looks like that, but in 2D, the diagonal elements are still 0, but the off-diagonal elements are not equal to each other. And so there's actually 2 modes. There's one in which the electric field is parallel to the structure. So imagine this case here. So the electric field is in this direction, and the Y magnetic field is in that direction. Under those cases, the apparent resistivity curve behaves just as you might have thought at this end here. So now we're on, this is a traverse along here. So at this end here, apparent resistivity is 100 ohm meters. At this end, it's more like 10 ohm meters. Okay, so that's nice, behaves pretty well. what happens if the field, so instead of the lightning strike over there, it's over there, and now I compute my impedance structure, and I get an electric field that crosses this way. Okay, so now we can go back to some of the fundamentals that we had earlier this morning, where we've got, let's say, current that's going to be crossing a boundary. Remember, if the conductivities are different, then what happens? Come on. Let's see. Manuel. What happens? Too late. It's way too late in the afternoon, I know. No idea? I got a current that's crossing a boundary, and I got. What happens? Choose a friend, help you out.
The current is equal, it change only the fields.
I think that was okay. So the current is continuous. So that means that the electric fields must change. And the reason electric fields change is because of charges. We're getting charges that are going to be built up here. So, gold star for Terry, please. Did we bring the gold stars? Unfortunately not. Okay, so look what happens here. So now we're going to look at the electric field. Goes up, and then changes, comes up with that. If you plot the apparent resistivity, it's a little bit wonky. So that's what happens in 2D. I mean, you can, of course, unravel all of this stuff with inversion, but when you're looking at the data, okay, if you're thinking 2D structure, you also have to think about, which way, which mode you're in. Is it a TE mode or a TM mode? In 3D, like everything else, things just get more complicated. Elements of the impedance tensor are built up, and there's no special symmetry, no special conditions. Let's just talk just briefly about measuring MT data. So the basic acquisition is something like this. You measure the E's and B's, and you'll have a remote reference. So remember, each station is just measuring a time series, right? So EX, EY. That's your time series. In this case, this happened to be a second, but and over many hours. And then you've got data at a remote reference. These are in time, and remember, as I said, they're kind of a mishmash, right? Because part of this might be due to this, this source. Part of this might be due to another source, and it's just all challenging. What you really want to do is to know what's happening in the frequency domain. But you can't just sort of take the Fourier transform of this stuff because it's a mixture of everything. But you have to do something different, and you somehow have to resort to the fact that, okay, on average, certain things happen, right? So you got all these sources which you think are kind of like a stochastic source, and so you have to treat your estimate of the impedances in that same manner. So this is kind of what you do as a quick. So let's take a time series and just divide it up into a whole bunch of windows. In each of these windows, we'll do a short Fourier transform. And that would give EX as a function of omega for this window, and one for that window. And then we could just go ahead and do an average, but we're going to bring in the fact that we've got a remote reference. So we're going to do kind of a cross correlation of EX with an HY with remote reference, as well as HY with the remote reference. So these brackets here are kind of like stochastic averages. We do it over this window, over that window. We just kind of keep doing it, keep summing up, averaging, and eventually stuff kind of settles down so that we don't have a lot of jitter and we feel like, okay, I've got a statistically good estimate of what the impedance is. That's our estimate of the impedance. When we invert the data, again, things are pretty much the same as we've been doing for the control source. The challenge here is that we really don't know the boundary conditions. So depending upon, maybe you've got some great big conductor that's channeling current in, or you've got some ocean that's far away that they could cause challenges with respect to the boundary conditions. But at the end of the day, the things that are done are pretty much the same as what we've done for all the control source. So I'm going to do a case history, geothermal energy, which after talking to Daniel seems like it should resonate with people here. So here's Iceland, sitting right on the mid-Atlantic ridge. So it's a spreading ridge. So lava coming up, and Iceland has got a lot of geothermal energy. Most of their power comes from them, and they're continuing to explore for more. It's helpful. In fact, I think it's almost essential in every time you use geophysical method that you've got a pretty good idea about the geologic structure, or a cartoon at least that helps you ground what it is you're looking for. And here's the one that works for the Icelandic environment. It comes about from the following manner. I suppose, so we've got a ridge that's spreading, so we've got high concentration of, let's say, magma underneath. You got a big heat source somehow. Got a heat source. Then you get water that's going to be circulating around through here, so water coming down, and eventually that gives rise to an alteration zone that's up here. So you get a layer of smectite, that's kind of a conductive clay that's sitting here, and you end up with a structure that looks like at the top. You've got kind of a resistive near surface region. Then there's this clay overcoat that's associated with things. And then underneath here, you've got a resistive core and then your heat source. In addition to that, there's hydrothermal circulation that's going in through here with hot water, and that is actually reducing the resistivity of this region. So this is resistive, this is resistive, the clay is very conductive, your reservoir is more conductive than this, and then you've got the heat source. Often what's looked for in geothermal energy is to try to find the bottom of this clay layer, because that's the region that has the potential for actually being a producer. In this case, we're not going to try to find the bottom, but we're actually going to try to find this region of moderate resistivity buried in that more resistant host. So the survey, this was done by Phoenix, MT instrumentation. So here's the coils for magnetics, and here's the pore spots for measuring the electric fields. And there's 133 stations, frequencies 300 to 1/1000th of a hertz. And there was a remote reference about 40 kilometers away. So we're interested in this region here. I'm going to talk about two stations, 1 and 3. I'm going to plot the apparent resistivities from region 1 here. And a couple of things. First of all, there's a red and the blue. So one is like an EXHY, and the other is an EYHX. So those two impedances. What we notice at the near surface here is that the red and the blue overlap. That just means that, okay, doesn't matter which way I'm looking, these are pretty much the same. So the Earth is 1D here. And then so this is high frequency here, low frequency there. As we go down in frequency, we're seeing deeper, and things become conductive, and they go resistive, conductive, resistive. Also, something's happening in here because the curves split, right? So what's happening, you got the two modes that are coming in, but both of them show, you know, high, low, high, low, high. Okay, so that's first order information. If we come down to this site here, then things change quite dramatically. First thing, the near surface drops by an order of magnitude. And secondly, these curves are split right from the get-go. I mean, at some level, they still have high, low, high, low, high, but you can see those curves have changed quite a bit. So there's quite a few things that have happened here. And also, this apparent low resistivity here kind of coincides with surface alteration and hot fumaroles and water and stuff like that. So now we do the 3D inversion. So we take this cube, and this was actually done by one of my graduate students, Gudny Rosenkar, in conjunction with the Icelandic Geologic Survey. Here's a cross-section that goes through, and you can see some of the things that we were already expecting. So it's resistive at the surface, and then there's this red conductive region in here. There's a red conductive region down here, and in here, there's kind of a blue background, thought to be the host, and then these regions here are kind of moderate conductivity. So if we put all that together and kind of make an interpretation that this red in here is that conductive clay cap, it's your heat source down here. The blues are your manifestation of your resistive core, and these regions in here are more conductive. I forgot to mention in this diagram here, this cross section is the one that kind of goes all the way through there. This is sort of a 3D representation trying to show what that resistive core would look like. And this region in here is the potential reservoir corresponding to that. So this image actually looks pretty good and pretty much in accordance with this. And in this case, there was a synthesis. There was a number of wells that were drilled. These wells are color coded in terms of temperature. So the purple, magenta is in here, indicate high temperatures, and the blues are low temperatures. And you see that, you know, there's kind of a nice correlation here. And this is the producing field here, and there's another producing system over here. So I think that was that's a really nice case history for kind of having, you know, you've got a model, and you can use MT, invert, 3D, make some sense out of it, and have it verified. So any questions? Yeah.
How about the lower interface between the conductor and the non-conductor place in the conversion? Because that's always a problem.
Sorry, this interface here?
Yes, that interface, is it well defined?
Oh.
How do you define well that interface that is always complicated?
Yeah, that's always a problem, right? If you think it's a sharp interface, then of course you can put that into the inversion and look for a sharp interface. If you have any kind of you know, well log information or something that, you know, you could pin the boundaries, then that's information that you could put in. Otherwise, you're just kind of doing,
because it's really amazing, because you have this 1 meter layer on the shallow part, but then you can see structures up to 8 kilometers.
Yep.
So it's huge.
Right. So it's that's right. But if you notice, the frequencies went down to 1,000.
Seconds?
Yeah, 1,000 seconds, right? 0.001 hertz. So if you look at the skin depth for something that is that low frequency, then you can actually get through there. And that's one of the great things about magnetotellurics, because you are in control of which frequencies you want, and if you need to see deeper, then you can use lower frequencies. Of course, your resolution, you don't have it at those really great depths, but you still get information.
The high conductivity, as far as I know, tends to elongate anomalies in the vertical direction, the conductive anomalies, tend to be elongated.
Mm-hmm.
In the shallow conductor there, the depth of that conductor is real, or is it elongated?
Oh, that I don't know. I think one of the ways to get some insight into that is to do a synthetic. Right, that's really the only way that you can decide or get some insight as to if you had this particular geology, and let's suppose you had a boundary that was really well defined, and you're going to discretize it at a certain level, and then you're going to use this regularization functional, then what do you see? That's the best you can do.
No, but you know how to collect that sort of?
I don't either. I think it was perhaps done over a couple of seasons.
There's one comment for what Fernando mentioned, that conductor should be constrained because we have the wells there. So you could do like a constraint inversion as well if you have information.
Yeah, this was not done with that, but you're absolutely right. If you had more information, you would be able to put that in.
I have one question that is kind of related. I know you said you were not going to talk about the inversion.
Yes.
But, you know, if that solution changes too much, if you change some parameters or balance something differently, like if you can still see the bodies that like some are more resistant than others, you can still have that solution if you change things in your inversion. Right.
So the question has to do with, basically the robustness of the inversion method, and if it was just sort of like, okay, I'm finally tuned, I got this one, I'm not going to go anymore, or whether there's a degree of latitude. So there's always some variation with parameters. There's three things that are really important. One is your misfit functional that you're going to use in your assignment of the uncertainties for the data. So that's a big thing. You need to work with that. If you change those, you're going to change answers. If the second is what regularization functional you're going to use, whether you're going to try to find something that's smooth or not, or how much a priori information you put in, because you might have a good reference model, or you might know this or that. So all of that goes into that part. And then the third is, now if you're formulating it as sort of a Tikhonov inversion, where you're misfit, solving the inverse problem by finding a minimum of your misfit plus some value times your model objective function, the usual way, then it's always a question of, okay, what is that trade-off? In most cases, you never know, well, in all cases, you never know where you should be. Often there's a little bit of a, kind of an L curve that's there, and you could pick different points in there. Generally, there's a region, you choose an optimum solution, but there's a region, you could have a little bit more structure, a little bit less structure. The big scale features more or less look the same. If you go too far off one way or the other, then things will vary. We actually have a nice tutorial that Lindsay will run through tomorrow, just to kind of illustrate some of those concepts. In this particular case, things were pretty robust. And in fact, the output from this code, okay, that was done at UBC, was pretty similar to what was done by a conjunction of Berkeley and MIT using an entirely different code. So, at that level, you've got different operators. I mean, the one thing about an inversion code, you can take the same data, the same code, and you can give it to two different people, And they might get out 2 different answers, right? That's all possible. In this case, we had 2 independent groups actually using 3 codes, or 3 3DM2 codes. 2 gave pretty similar results. The third one was a little bit off, but there was reason to understand why that might have been. So, yeah. So I mean, actually, in this case, I mean, I think that's a pretty stable result. If you start to get a little picky about, okay, where is that boundary and that now, you'd be on a bit more shaky ground. Is there another question? Yeah.
Was that inverted with a Siricúmbara form?
With what?
This is a really complex last name of one guy that has a MT.
Oh, yeah, we're shy. Yeah.
Siricúmbara form?
Yeah, that's his last name. Yeah, no, this was not. His code was actually the outlier. But I think it was really the effects of topography that made a difference here. But these codes, this code that was done is a finite volume code, and it has topography in it. Again, one of the things is we've been traveling around, we're starting to see how many people are connected in one way or another with the MT problem. And I think that makes it an interesting problem to kind of focus on as a community to make sure things are in open source and people can communicate with each other about that. And we'll talk more about that tomorrow, but from our perspective, they've developed SIMPEG algorithms that can invert, not this example, but other examples have been done 3D inversion using that code. And there's still more refinement that could be done. But so there's both the 3D simulation and inversion, and then there's also the aspect of going from the measured time series to the impedances. Again, there's a number of codes around there, but they're older codes. Not that makes them inferior. Developed in Fortran, but it's basically it's hard to get in and change things, or it's hard to get in and know what they're really doing. And I think that's why the time is now so right to say, okay, look, those codes are great, but let's maybe make a new generation of codes that are open source, that people can try, that people can contribute to, that we can take example data, and everybody can be working with the same data, and really kind of up the game a little bit. And I think if we could do that as a community, that would be very beneficial. So let me show you a case in your own backyard. Santa Cecilia, it's a big porphyry system. So here we are. Let's see, so Santiago is right about there, is that? Right about the edge of the box. Here's Buenos Aires. You're basically horizontal, right? Yeah. Oops. So you're right at the edge of the box. So there's your mineralization belt here that has gold, copper deposits. This is a big sign of alteration that's going on. So you got intense hydrothermal alteration, over 1,000 meters of that, and here you got gold, silver, copper. Again, a cartoon is really effective. And here's one that was put together by a guy named Silito in 1995. And we've been interacting with people who are working on this Quantec and their interpretation of the data and what's going on. And this model actually seemed to coincide pretty nicely. So our question really is, we've got this kind of a system. We've got an initial stock that's coming in here. It's a porphyry stock. There's alteration products that are going on. We've got potassic alteration, we've got propylitic alteration. There's regions of high sulfidation up here, and yeah, the question is, can we find something like this in this environment? And what do we do? The alterations that occur are generally magnetite destructive. So one of the sort of tried and true ways of getting some information about mineralization is to look for magnetic lows in a region that has got, you know, a background high magnetic susceptibility. And when that was done, so this is a 3D inversion of ground-based magnetic data. It ended up with this outside ridge here indicating a region being the outer limits of low susceptibility. And inside here, there were two regions that had somewhat moderate susceptibility. But it was felt that this was the mineralized zone. And then there was a geochemistry that was done and identified a number of copper-gold anomalies within here. So what they wanted to do was to go out and test the this MMI result and yeah, to see what they could see. So they proposed a CSAMT experiment. So we've talked about MT. The A is audio, so that just means that you're back into a frequency band that we could almost listen to. And control source means that you're responsible for the source. You're not putting out, not waiting for the lightning to strike. So when we looked at this example of what Soto's model was and the alteration products that were obtained, there was a number of sort of correspondences on here with respect to what each of these units were. So it was actually felt that this was a pretty good representation of what's going on. And then we've got rock units. There's the host, there's the stock, there's the alterations. And we're going to concentrate on the resistivity. I'll mention chargeability. We're actually not going to get to IP until tomorrow, but so the host rock is very resistive. The stock is maybe moderate resistivity, and the alteration zones are low to moderate. Chargeability is it's a manifestation of the fact that the rock can has got electrical resistivity. It's frequency dependent, or effectively there's a change in the resistivity as a function of frequency, and the result of it is there's a tendency for charges to build up. So the rocks kind of act a bit like a capacitor, and then that gives rise to an electrical voltage. So we're going to that more detail, but the point is that the alteration products are chargeable. Here's CSAMT. We've got a transmitter sitting out here. We're measuring electric and magnetic fields, and the receivers need to be at least several skin depths away. So that's what we mean by far field. So far field means that, okay, you're away from the transmitter, but your distance away depends upon how many skin depths. If you're 5 skin depths away, you're in the far field. So their transmitter was about 3.5 kilometers long, and their frequencies were 2 to 9,000 hertz. So that's why it's called audio, right? So you can listen to, 100, couple thousand hertz. Yeah. And the receivers were about 10 kilometers away. So here's the initial discovery. So they did the CSAMT experiment. They got the resistivities, or they processed the data as magnetotelluric data. And here's a couple of lines. So it shows some regions of high conductivity. That's in red. And here's a couple of cross sections in 3D. You can see there's this conductive, it's sort of a horseshoe thing that's going around here. So there's definitely, a real conductor there, and that corresponds. Here's the geochem data. So here's the gold anomaly outline, and here is the copper anomaly, and that conductive region that was obtained is kind of underlaying on this, so that you can see there's actually a nice correspondence between the geochem and the electrical conductivity. So that's good. So the hole was drilled through that conductor, and where you had the high conductivity, so there was significant copper. This hole is actually the well here is color coded to copper values. So the red is the result of the CSAMT, and this drill hole, which went through that conductive region, continued to go down. So it extended beyond, and there was sort of copper significantly down there. And the same is true with another cross section here. So there are actually two drills. So that's sort of good news. I mean, actually, it's very good news. You've got a conductor. You drill it. There's copper. You keep going, and you still find more. So the CSAMT, because they went only down to 2 hertz, could only see a certain depth. So that led them thinking that maybe there is something deeper, and we should have a different experiment to work with that. So here's basically where we were. They got the ground magnetic data, anomaly, did the CSAMT, 2 drill holes, but they need to see deeper. So now they use, this is Quantec, so it's a 3D Orion system, which does both DCIP and MT. So this is kind of how that works. So now you're in 3D. Now we're back to that situation where you just don't know where things are. And so you want to try to make sure that you've got as maximum coverage as possible. So for those of you who have a seismic background, you know also what you're doing. You 3D, you need 3D coverage. Okay, so you want to make sure that every voxel in your 3D model, it's got some reflectors that are coming off of it. So that means different orientations of your transmitter and receiver. The same is true with DC resistivity. You need to set up something. So in this case, take a region a couple of kilometers by a couple of kilometers, and you populate it all with electrodes. Some electrodes are going to act as current electrodes. Some are going to be potential electrodes. And then you're just going to measure a whole host of data. And then this is a sort of a cloud representation of where you might be sampling. So it's just like doing an apparent resistivity, between 2 points, and drawing lines down, then plotting a point there, but then having this as a volume. And then you look at the sequence of points and decide, okay, has everything in here been adequately covered? So then that gives you first order estimate of what's there. So for the DCIP, there was 539 transmitter locations, a couple hundred receiver dipoles for each of those. In addition to that, they do the magnetotelluric. So there's about 100 MT sites. And orthogonal induction coils. And the way it works during the daytime, they acquire the DCIP data. And then at night, they just let things go and they record the MT data. So they just kind of keep cycling through that. In fact, that's an acquisition system that is being, similar acquisition system is being deployed a lot. For instance, in some of the work in the Red Sea, I haven't shown you that case history, but they've got controlled source. They're towing some receivers, or the receivers could be on the ocean floor. And they're towing a source, and the response for that source are recorded at these stations, but then they leave things quiet for a while. So now you're just having natural sources come in. So now you're recording bits and pieces of that, and then you fire the source off again. So you kind of got intermittent. You're measuring continual time series. Some of it has actual information from the source. Some of it's just natural. And then you just work with that, build it all up, and eventually you collect MT data as well as the CSEM data. So this is somewhat the same flavor, except you're using day-night. So the DC resistivity data, here's your apparent resistivity, 150,000 points. Can't do much with that. You need to invert it. And so you do a 3D DC inversion. Here's your electrical resistivity model. You do a pi slice out of that. You can see there's a conductor. If you look at the electrical resistivity at 700 meters, you can see that there's kind of an interesting geometric shape here. It's kind of a circular pattern here. So this is the highly conductive region. And at 900, there's a circular pattern here. It looks like there might be another ring in here. So that's something you get from the DC. We also have IP, which I haven't talked about, but that's collected at the same time. Need to invert those and end up with a chargeability model that looks like this. And it's kind of interesting to look at the relationship between the two of them. So in the resistivity, we have this high ring of conductivity here. If we take that contour and put it on here, we get something that looks like that. The chargeability looks like it's kind of got a bit of a ring here. Superimpose that on that, it kind of comes out in there. And at 900 meters below the surface, again, here's the high conductivity that goes over here. Here's the high chargeability goes in here. So this high chargeability is kind of going in between the two regions of high conductivity. Yeah.
So could you just read the scales on that resistivity?
Oh, this is 10. This is 40. That's true.
And the resistivity?
Oh, so chargeability. So resistivity. That's 1,001. So there's 3 orders of magnitude. So now we come to the MT data. So we got 100 MT sites. Yeah, basically 450 meter spacing. Here's the important part: 250 hertz to 1/1000th of a hertz. So now you should have some deep penetration because that's a fairly long skin depth. So the data were inverted in 3D, and here's a couple of sections. So there's something that's really conductive. And we're going to compare that with the DC resistivity. So DC resistivity should certainly be seeing shallow and then down to a certain depth. And then if you compare that with the MT, the top part actually coincides, but the MT extends deeper. And the same is true with the MT and the CSAMT. So here was the CSAMT image, and now the MT extends down to greater depths. If you look at the MT image, so here is the contour. So that's anything less than 10 ohm meters is inside these contour values. And here's one of the drill holes comes through there, and you now have mineralization right up to the end of the hole. And here, this one is just kind of sneaking through. So been mineralized all the way up to there. So the outer volume, and if you took a shell of anything less than 10 ohm meters, was moderately effective in actually encompassing the region of significant copper mineralization. Yeah. So that was the MP. If you want, how are you doing? I can talk for another like 15 or 20 minutes about Z10 because that's also natural source. It's a logical time to talk about it. So remember, we're talking in the MT problem. You got these natural sources. So you've got currents that are induced in the ground, and we had a transfer function between E and H. Okay, that's one transfer function. But you can make a transfer function between any two fields. Doesn't matter. It's just it's a representation of how if one thing changes, how the other thing changes. So that's all it's going to tell you. So another possible transfer function is to look and see, okay, how does the Z field change in comparison with the horizontal fields? Fair enough. In this Z-axis tipper EM, tipper comes from an old terminology for using the ratio of the vertical to the horizontal field. And why it's interesting is that as much as you're just sitting out in the middle of nowhere, and you have a 1D structure, okay, then there is no vertical magnetic field. All of the currents are just. However, suppose you had a wire, so that there was a current that was induced in that wire, then there's going to be a magnetic field associated with that current. And then over here, there'd be a vertical component of the field that would be either up or down, right? So then there's a relationship between, or that value of magnetic field vertical component to a horizontal will have some significant number. If you were on the other side of that wire, now the vertical component of the field changes direction. So what was positive over here is now negative over here. And so that relationship is changing. And so if you plot these things in such a way, then you can see how the magnetic field is kind of tipping. It's changing, okay, because of this, how the vertical component is. And hence, that was sort of the reason for the word tipper to come in. And the old geophysical system used to do is called AFMAG. And they actually had coils on planes that would try to measure where that vertical component is and look at the ratio of the vertical to horizontal component. Anyway, you could do this in many ways, but the way it has been recently developed by Geotech is they have a base station. So they measure the horizontal magnetic fields at a base station. And then they measure the vertical component of the magnetic field with a large loop that's just flying back and forth. So this transfer function now is just like basically a vector, and it says that the magnetic field at any location here is dependent upon the reference horizontal electric or magnetic field at the reference location, okay, by this amount plus a certain amount of the HY component. So it's just a relationship between the vertical component at any location and then what's happening for the two horizontal components over there. That's it. But that relationship is definitely going to be affected by whatever conductivity structure you have. So embedded in here is information about the electrical conductivity, which you then need to dig out. For practical reasons, you can really only measure between, let's say 30 and 720 hertz. This end is difficult because I mentioned very quickly that there was a dead zone. We just end up with low energy in these higher frequencies. So it's really difficult to measure. At lower frequencies, you start to get into problem, the aircraft is going at a certain speed, and you need a certain amount of repetitions in order to get anything. Since the time that we did this, the aircraft can definitely record 15 hertz. And now, the last time I talked at Expiration 17, they were saying, yeah, they think they can try to get down to 7.5 hertz. So they're getting rather lower and lower frequency. So how does this work? We've got a synthetic example here. So let's suppose the electric field is coming in this way. So now, we've got these plane waves that are impinging, and the electric field is going, let's say, in the x direction, and we've got a conductor here. So now we've got a current that's going in like this, and then the magnetic field associated with that would be up here and down here. So if I looked at the vertical component of the magnetic field, it would look like that. Similarly, if the electric field is pointing in this direction, now my magnetic field would be coming up here and down here. So you can see how, depending upon which way you're driving currents into something, how the magnetic field would change. Then what we did this morning, we spent a lot of time on looking at responses from frequency domain system, and we said, well, they're going to get partitioned. Some of them are going to be in the parts of it in the real, parts of it in the imaginary. And if it's really conductive, it should be much more in the real. So that's what we have here. So now you've got a real and an imaginary for both of these Tipper values. So that means at each frequency, you're going to have like four data maps. Okay, I'm going to have sort of two case histories. One is a synthetic from the Noranda district in Canada. The other is Balboa copper deposit in Panama. The Noranda district in eastern Canada has been a very productive mineralization zone for over 100 years. And here's a region that's like 20 kilometers by 20 kilometers more that has about 20 economic VMS deposits and a whole bunch of organic gold deposits and a lot of structure. So a lot of people have worked on this, and because of that, they developed a geologic model that actually had 38 geologic units. Okay, so now we've got a big 3D region, 38 geologic units. So what we're going to do with that is to populate that geologic model with electrical resistivities, and then we're going to go ahead, forward model them, and invert them. So we're looking at frequencies from, let's say, 32 to 720 hertz. And here's the true model. So it's a 3D model, but we're going to take a slice of 275 meters depth and look something like this. So the blue is resistive, the red is conductive. And so you got these units. If you look at the data, so here's your transfer functions, TZX. So this is the real part, 90 hertz, looks like that. Imaginary part looks like that. If you look at TZY, real and imaginary. So there's 4 pictures. Okay, what you really want to do is have this guy, and you've got these kind of images here. So you can see that there's some data that look like a little bit like that, but by and large, it would be hard to do. Plus the fact that you now have like 6 different frequencies, so that's another 20 maps. Anyway, you can take those data, and this was actually done by, well, he's a postdoc now, or he's got his own company, one of my graduate students, and Elliot Holtum, who did this for his PhD. And this was one of, I think, the first 3D inversion of Z10 data that we know. Anyway, so the recovered model looks like this. And if you do a slice of this at 275 meters, it actually looks like that. So if you compare the recovered model with the true model on the same scales, you actually do really, it's when we first saw that, we were actually remarkably surprised. I mean, this seems like just a great geologic representation of what that true geology was. In addition to that, there was a few deposits, so there's mineralized deposits. There's a couple here in three-dimensional volumetric form. They look like this. So here's the true deposits as they were put in, and the recovered from the Z10 look like this. So you've got manifestation of this, and this that are showing out from the Z10 data. So that was, I mean, I think that was really encouraging, and I think it shows a couple of things, and especially one of the great powers I think for the ZTEM is that it's a great geologic mapper from the point of view of near surface.
How good does that data have to be that?
I mean, this was a fairly robust operation.
Did you put the errors on?
Yeah, we did. So there was uncertainties. I can't remember what they were, but always we do a floor plus a percentage. One of the more challenging things with inverting Z10 data is when you get data to actually figure out, okay, what is a reasonable uncertainty? And also with Z10 data, it's challenging sometimes to get the absolute conductivity, right? If you only have a layered space, then the vertical magnetic field is 0, so there's no information about conductivity. And if you have something that is, basically layered, but it's got some inhomogeneities in it, you can actually fit the data by having, a number of different background models, and it will still give it to you. So finding the absolute conductivity is sometimes a bit more challenging. Interestingly enough, that problem is helped if you have topography. So if you've got lots of mountainous terrain or something like that, then that actually helps get things. It also opens up the door for, because of the interest in geothermal energy here, where magnetotellurics is really useful. Combination of ZTEM to help with the near surface structure, and perhaps fewer MT stations, which are expensive to acquire, might be a useful scenario in some cases. We can go through this one fairly quickly. So this is a result that we obtained from Jean Legault with the use of ZTEM. So the area is in Panama, and the Balboa area discovery is kind of sitting out in here. It's in an area that there were a number of deposits that already existed. So these guys here were already kind of known deposits. Most of these deposits were actually found by exploration programs. It was to see if there was anything that was nearby that could be discerned. So here's a kind of a geologic map of the area with the Balboa deposit here. Previous helicopter time domain EM surveys had been not successful in finding this. So really the question was, okay, can ZTEM see the mineralized zones beneath a conductive saprolitic layer? So that is one of the big challenges here. There was a 20 to 30 meter thick clay region of saprolite that makes it difficult to see through. So every time you've got something below a conductor, then you're going to be challenged. So the basic quantities here for the mineralized zone is that it should be high conductivity and low magnetic susceptibility. Again, these alteration products or alterations are eating up the magnetite, so you're kind of looking for that kind of combination. And then it's all got this highly conductive saprolite up to 30 meters thick at the surface. So from the point of view of the things that you're looking for, you've got two things that have a low resistivity, the saprolitic layer and as well as the mineralized layer. So it might be challenging to discriminate between the two. So the survey was a Z10 survey like we've just used, 6 frequencies, airborne receiver, and a base station. This was one of the things that gave them some degree of optimism that this could work. So this was a 2D example, so it's a synthetic. So we got this thin, well, 30 meter thick layer of highly conductive stuff, and then now you put down a conductor underneath here that is your target. Collect the ZTEM data artificially and invert them, and you get something that looks like this. So that gave them some confidence that they might be able to see what's there. I think the thing that helps in this case is the fact that this saprolitic layer is like it's just a layer. Remember I said that the ZTEM is insensitive to a horizontal layer, so it's not going to. It's basically blind to that. And if you've got something down at depth that's going to cause a disruption, then that's going to be the first order signal that you see. So you just need to have like low enough frequencies that you can kind of see through this thing. But once you do that, then this is not so harmful. And maybe that's the reason that the time domain EM signals were challenging, because you get at a late enough time, even though you get currents that are generated here, you still got a lot of currents that are sitting in here that are actually affecting the signal. So here's our chipper. It looks like this. And these guys are obtained through a process that was similar to what we talked about in MT processing. Yeah, so this plot here is just the elevation model. And then here is the total field magnetic intensity. Remember, you're trying to look for regions of low magnetism. So this is the TMI map, and then it's reduced to pull. So there's a couple of things here that are noticeable. So here is one deposit. Notice that's got a low susceptibility. Here's another one that has a low susceptibility. Balboa, which is over here, it's kind of betwixt everything. It's got kind of a high susceptibility or magnetic, I'll say magnetic field value here compared to this. So it doesn't really. Certainly doesn't stand out in the magnetics. ZTEM, so here's the real and the imaginary at 90 hertz, and so that's TZX, and this is TZY. So again, 4 different maps. For the ZTEM data, if you have a wire, well, exactly like we had talked about before, if you have a wire, a current going through there, then the vertical magnetic field would be positive on this side and negative on this side. So it sort of does an inflection. So what they do is a phase rotation of this, and then at least puts the data maximum over top of the location of current. And so that's the chipper data at 360 degrees phase rotated, and that's the real, and that's the imaginary part. So now they do a 3D inversion of this, and they find a in this region here, there's a large conductor that's imaged depth. So this is at 500 meters. And if they did a cross section along this line here, you end up with something like this. So there's this large conductor. So the saprolytic layer is up here, and then there's this large conductor that's going there. And also the magnetic susceptibility has this sort of low value in here, so that kind of coincides with this high conductivity. So high conductivity, low susceptibility, starting to look very favorable. When they did the drilling and they were able to outline the mineralized shell, that kind of sort of corresponds to this, and then they superimposed that on top of the conductivity or the susceptibility, you can see how this region here outlined kind of corresponds there. So that's the background here is the conductivity obtained from the inversion, and that actually matches pretty sensibly. So it's kind of similar to the synthetic model. So I think that's that was sort of the takeaway that airborne time domain data could not really see through that saprolite, but they were able to find a kind of a anomaly that was co-located with a region of low susceptibility that actually defined that low deposit. Yeah, so there's additional material, Red Sea work, landslides, lots of stuff. Anyway, yeah, for those people who are seismologists in the Red Sea, this is what they're up against. This was the seismic data that they were getting, and this is a sign of the geologic structure that was obtained. So they did magnetotellurics and controlled source EM, and were able to get images out that looked like this, co-located with the seismic, and actually corresponded to some real hole information. So we don't have slides for this one, but the content is on that for people interested. Anyway, that's probably enough for one day. I'd say you guys are to be congratulated for staying awake. Here's what we're going to do for tomorrow. I'll pick up. We'll do a few things that we haven't done today. If there's any case histories that we've kind of glossed over that you feel would be interesting not only to yourself but maybe to the Chilean group here, please let us know, because we can go back and do that. Things that we've missed are the GPR and the induced polarization. Something else we haven't talked about is basically a DC resistivity experiment, but taking the early time data and recovering the electrical conductivity from it. Usually these early time data are thrown away, but we've got some examples, synthetic especially, that show, okay, if I had actually measured those data, used those as as part of a time domain EM experiment, I could actually get some very good information out. We have a case history for kimberlite deposits that I think people might be interested in because it's got a use of airborne IP. It also talks about EM decoupling, which is a big problem in general. So the question is, so after we've done the IT, okay, then we kind of realize what the full, you turn the transmitter off, and then you've got EM signals from induction, but then you also have IP signals. Right? And now there's a time window in there where those things are kind of overlapping and it's kind of hard to figure out what to do. So we're proposing a way of doing that and have applied it in a synthetic case to ground data and in a field case to airborne data over a kimberlite deposit. I think that's kind of interesting because it also then takes things to a new level of looking at multi-physical properties. So not only conductivity, but resistivity, density, and using the IP as like another physical property. So there's stuff there. It's getting a bit more technical, but I think it also is kind of interesting, and very happy to talk about that. In addition, we'd very much like to hear from you about what kinds of problems you're working on. Doesn't have to be long, but we just want to capture that. Like, okay, this is the problem that I'm working on, this is what I'm doing, and this is how it might be connected with EM. We'll capture that live on YouTube with your permission, and yeah, and then it'll be there for posterity, so we could kind of find out what problems people are working on, and that'll actually help with communication. Our goal is to try to help foster development of a community where people can work together, and those have been really valuable in that. So we have a blog. Yeah.
Yeah, so I'm sure most of you have seen this site. All of the course material can be downloaded here, so the slides and everything from today are on, if you look at the schedule. And then the blog is here. And so we've been writing about every location that we've gone to. There's some pictures, a brief summary, but then one of the important things really is the DISC Lab Day and seeing what people have talked about. So for example, in Vienna, you can go in and see what kind of problems people are working on. So there's a lot there with landslides. They've got their own airborne EM system. And so some people were talking about that. There's a case history that they were talking about actually looking for karst structures in Mexico. So it's a really interesting way to get a bit of a picture of what's going on worldwide with EM. And so we've been trying to capture that as we go. And so that's what we'll be doing tomorrow. So feel free to check it out and you can see what we've been up to there.
So I don't know, it'd be really helpful for us to just get kind of a show of hands as how many people would be willing to just talk for just a couple minutes, say, hey, here's my name, this is the problem I'm working on, it's what we're trying to do. One? Wow, overwhelming response, right? So here I am, so I'm talking for 8 hours, and we're asking somebody to talk for 3 minutes, and it's like, oh no, God, can't do that. That's like way too much, right?
It is meant to be informal, like 3 to 5 slides.
Yeah, just something to kind of give us some flavor for what kind of problems you're working, whether it's geothermal, and then what's the context of geothermal, mineral exploration, what it is. I mean, and especially as we're in Chile, I mean, you've got problems with this caliche, and there's some challenges there. Let's just air them out so that we at least have come back with some sense about what people are trying to do and what the problems are.
Probably have to hear, but I can shoot your name now if you wanted to discuss.
Yeah. Who else is here from BHP?
I think none of us are able to come tomorrow.
Oh, you're
tomorrow.
So what about all these masters and PhD students? Do you not have problems? Yeah?
I can ask also my students to present some.
That sounds good. I think you you asking your students to present something is probably more effective than me asking your students. Yeah. Anyway, I ask you to do that. It actually might even be helpful for you to stand up and just say, look, okay, here's my problem that I'm working on, and here's what I'm thinking about for EM, or I'm doing this EM, or whatever. That would be really good. Then the remaining part of the day will take you through GeoSci, our main website. Lindsay will show you what the components of that are, and just talk a little bit about SimPeg and programming, show you some examples, how to get on to work with the apps, how they're programmed, and they've got some tutorial examples on one-dimensional MT for doing both forward modeling and inversion. So lots of stuff, but our mission here is to be effective, right? Everybody's busy, and we don't want to spend time just talking about stuff for stuff's sake, right? So we're trying to focus in on those things that might really be meaningful to you. So we need to have your feedback with respect to that, and give us some guidance on what you want, because you can see we've got tons of stuff, and so we need to have some participation. And yeah, for those people who will not be here tomorrow, even though we're not completely finished, can I get you to fill out a feedback form? This is always very important. It's a thing that people hate to do, but it is actually important. Yeah, everybody else, we'll hand them out. We'll hand them out tomorrow, and then at the end of the course. How many people here are doing any coding in Python?
Are you guys all? So any other questions for people still here? Got a question. Your question?
Personal question about programs. Do you have sometimes something to increase on labs or see empty data like Hitler or things?
We do have some plotting utilities, so I can point you to some examples of where those are. We don't necessarily have it's not streamlined, so if you just have a data file and want to plot it by drag and drop, I mean, we don't have anything like that there. But we do have some utilities for visualizing. Yeah. So, I don't know if that answers your question, but there's some things around.
So who here is working on geothermal problems? Raise your hand. Okay, so we can get at least one of you to talk about geothermal problems, Daniel, and okay, good. Okay, so couple talks on geothermal, and then mineral exploration. So could each of you have something, or you're not gonna be here?
He can.
Okay, perfect. Jerry, do you have any comment? You're not gonna be here tomorrow, right?
I'm not sure.
Oh, okay. In the event that you can't come, do you have some comment about, I don't know, things that, are, I don't know, that are important problems that yet need to be solved, or important places where electromagnetics could be applied that haven't been applied? Any comments?
I don't think there's any lack of places that have been applied. We have problems that we can't solve, but it's the one I'm thinking of the moment has to do with the fact that the EM techniques really not best suit conductors, so we have to want resistance problems that we want to find, like weathering profiles and that sort of thing. It's not very conductive. They're very important in some operations to map them, and nothing can. They're everyone's blind zone, they're too shallow at the seismic. They don't suit GPR, etc. Well, it's a big problem in mines, it's not an exploration problem.
Okay.
The biggest problem we have in this country, Doug, is picking EM from IP.
Yeah, so what is the state of art or practice with respect to EM coupling, or are you just trying to invert for general complex connectivity, or?
Well, what we can do now with that code and scripts is to solve the EM problem. And if that solves the data, then there's no IP.
Yeah.
So we can do that. But it's a fairly big problem to run routinely. Kerry normally runs that on a couple hundred cores. I only run it on 8. So that's all.
And that's 2D code yet too, right?
2.5.
2.5, yeah. So these are all just, they're grounded sources at, in your case, just at the surface, and you're measuring.
So we've had some luck. I mean, we have, in some instances, found we can do IP at 1 hertz. There are other cases where it's quite true.
Okay. Yeah, so your procedure for getting rid of, for decoupling is basically find a connectivity structure, estimate responses, and subtract. Yeah. Okay, so that's minerals, geothermal. What about pollutant? Yeah, go ahead.
Groundwater. So we don't have much to say with regard to mineral exploration, but I guess we can offer to show a few slides on time-lapse resistivity imaging on the filtration test into the unsaturated zone. So what we did is we injected 60 liters per second into the unsaturated zone and had time-lapse imaging running 1 snapshot per hour, something like that. So it's quite interesting to see how powerful the time dimension is with regard to DC resistivity and repeating DC resistivity surveys over time.
Oh, that would be very interesting.
So we've done that like long time ago, so we can show that maybe in a few slides. It's quite interesting. There are lots of things happening in resistivity changes when it comes to wetting and to drying. According to maybe some of you guys know infiltration tests or something like that. And it's pretty insightful to look at the data in detail. What happens in 2 meters depth or 5, 10 or 30 meters depth below an infiltration point that is being fed by 60 liters per second over 2 or 3 days. So we have got a time-lapse sequence of 100 or 120 images once per hour. So, and it's quite interesting to see what's going on with these observations. Something methodological, just brute force.
Yeah. No, but that would be very interesting. And that hysteresis, I'm trying to remember where the hysteresis was coming in Germany.
That was ice.
That was ice.
So it went from melting.
Right, yeah. Okay, so something on, what else about water issues? Is there pollutants or aquifer delineation or any of those things?
No, this was just with regard to technical feasibility of infiltration.
Yeah.
With regard to the topic of artificial aquifer recharge.
But yeah, so that point's well taken. But I was just wondering, with anybody else, are there other issues in Chile that are really important with respect to water issues, whether it's saltwater intrusion or whether it's pollutants or whether it's aquifer delineation? What about waste dumps?
I can show something.
Yeah.
I work with this project of it's supposed to be future for some people about calculating the hydraulic conductivity from IP signal.
Mm-hmm.
I can show a little, I don't have much to show because of confidentiality, but I can show something.
Oh, that would be good.
Yeah.
Yeah, we were just in Germany, and yeah, there's a lot of developments there that are really quite interesting, and also in Aarhus, the Danish group. What about waste dumps? The reason I ask about that is that the IP signature from waste dumps seems to be pretty consistent and often quite strong. So there's the potential for using IP and like DCIP experiments to delineate between leachates and wastes. And also there's the potential for monitoring and remediation. Issue? Mexico City was a huge issue, right? And also in places in the United States, like Tucson, it was a big issue. Because these cities started out small, right? And then you're living in a city and you got to get rid of your garbage, right? So you truck it up a couple of kilometers, dump it in, good, go away. But 2 decades later, the city has kind of overgrown that, so then you continually expand farther. And if you look at a map of Tucson, you see that there's just a large number of waste dumps that are inside the city limits, and that causes all kinds of problems from the point for both health. Potential contamination of your water, as well as just land values. I mean, if you own a property that somebody now decides, oh, there's a waste dump underneath, you kind of lost a lot of value. So there's just a number of interests in trying to find waste dumps.
No, but I think if we start measuring around the waste, we're going to find that for sure.
Yeah. Okay, that sounds great. Listen, thanks everybody for coming and staying awake. Good. See you tomorrow.